Welcome back. In this lesson, we're going to look at the Milky Way. And the Milky Way, our hometown. We're going to see the shape of it, the way that it's constructed, and the way that it was determined, how it was mapped originally. So pretty interesting stuff, I think. Here, let's look at it. Suppose your task was to map the entire national forest from your tent that was located somewhere in the forest, but you could not leave the tent. You could see some trees around your campsite. You could see that some trees were farther away, but you didn't know how far. You could kind of see basically a bunch of trees, but you couldn't see the trees for the forest. You couldn't see the forest for the trees. That's really what we are in the situation where we're looking at all of the stars in our galaxies and farther from our galaxy, but we're not allowed to change our perspective at all. So we're looking at stars, trying to find out how far apart they are, how far away they are from us. What is the three-dimensional map that we are a part of? And from our location only is all we have to work with. So it's very difficult. And for ages, stars were simply considered to be at a fixed distance from the Earth, kind of on a ceiling, painted on a ceiling was kind of the idea, at some kind of a limit to what we could see. Back in the 1920s, Edwin Hubble specifically, along with some other pretty amazing astronomers, were able to essentially use stars that were unusual in order to map distances. So they realized that some stars change their brightness over time. So now some of them are very quick. They might get bright and dim, almost like a lighthouse, over hours or minutes, sometimes days. And these variable stars were able to be determined based upon the brightness of how far away they are. And that math relationship enabled astronomers to map at least some stars in the Milky Way. And then from little and little, bit by bit, they were able to determine a map that where the Milky Way was something that we're embedded in rather than something that we're looking out from the outside. So the variable stars that we're looking at are in the giants. If you remember the HR diagram, the upper right of the HR diagram had stars that were very cool, so they were red in color, but they were very, very bright. And some of these pulsate because they are working harder to burn bigger and bigger elements, to fuse them together into new elements. And as they're doing it, essentially it's like an engine that's grinding and overheating. It's pulsating. And so this expansion of gases and contraction of gases is leading to certain times of light being spit out at a higher intensity and then sometimes lower. There's two major types of variable stars. You have the ones that are short, where they get bright and dim in a very short time. These are called the Lyrae variables, or the RR Lyrae. It comes from Lyra, the harp, which is in the summer sky. And then you have the Cepheid variables, which are farther away. Now, this is where it was in these constellations that these first variable stars were found. They're all over the place, but the very first ones were found in these constellations and were given these names. So as you look at them, they are simply going to get bright and dim, bright and dim. And then the math is simply by measuring how long the pulse takes, they can determine the absolute magnitude of the star. And if you know the absolute magnitude of the star, you can find the distance from the Earth. That's the idea. So just from logic, if you were to have the concept of attraction by gravity, just that idea is that you're going to have more collection of mass in the center of the blob than you would on the outs. And then often when you have contracting material, they're going to start to move. They're going to start to spin in a circle. And so consequently, you can make some guesses that the galaxy is going to be somewhat circular, somewhat flattened, somewhat widened in the middle, almost like a fried egg. So by looking at that, you can kind of make some guesses. And then as they made measurements, they realized that their measurements were in line with these ideas very, very well. Eventually, in the middle of the 20th century, it was determined that the center of the galaxy is about 26,000 light years away, and it's roughly in the area of Sagittarius. So Sagittarius, if you remember, is the teapot. And so the steam right at the top of the teapot that starts the Milky Way, that's where the greatest brightness is, the most light pollution. And we're looking in that direction towards the center of the Milky Way Galaxy. So eventually it was determined that the shape of the Milky Way Galaxy is a disk, a spinning disk with an enlarged center, with a number of globular clusters surrounding that center. That's going to be called the halo. And then the arms of this disk are pronounced so that it's not just a flattened disk, but it's actually spiral. It's a spiral disk, so it's kind of spinning with arms. And there's 4 major arms of the Milky Way Galaxy we'll look at in a second. Okay, so we're going to see that there are 4. We are in the smallest of the arms. We're in the Orion arm, and you can see that these are named after constellations too, in terms of the major place that you're looking at as you're looking at certain constellations. You're looking at the majority of the stars in that particular arm. So you have the Orion arm, you have the Perseus arm, you have the Centaurus arm, and you have the Sagittarius arm. So, Centaurus is the Centaur. It's a little bit below Sagittarius, so it's in the southern sky. The other 3 are we would see the northern sky. So the sun is located in the Orion arm, which is the smallest, and it's about 2/3 away from the center. So that's actually where you would want to put a planet if you wanted living things to be on that planet, because the amount of radiation and the high spectrum radiation, which would be very dangerous to us towards the middle, would be too intense. So we're shielded. Our distance from the center is shielding us from these damaging rays, and all of the distance between it is helping us. So we're located in a minor backwoods neighborhood around a spiral galaxy. A lot of spiral galaxies that have been seen through the Hubble scope also have a bar. So it's not just a pure spiral from the center, but it's almost like a rotating, like a baton that's being rotated around its center, that might have streamers on the outside of the baton, where there's a bar across, and then from the edges of the bar you have the spirals. It probably is not the case with the Milky Way, from what we can determine. It's just a normal spiral galaxy. The halo is not just the concentration around the inside of the galaxy where the most mass occurs, but there are globular clusters that kind of surround the outside. So there is a kind of a haze around the disk, making it almost like a ball. These globular clusters, remember, are stars that are very, very close together, almost in a wad, where each of the stars are exhibiting a pull on each other. It was thought that these are older if that can be determined. Older stars, with the younger stars kind of being in the swirl in the inside. The inside of the galaxy, it's been determined that there is a supermassive black hole, where as different different star groups and stars come together in the inside so intensely that there's so much gravity that even light does not escape. And so a supermassive black hole could have been formed by an explosion, and then just the coalescence of so much mass in an area that you would have a black hole. Population 1 stars are found in the disk itself. So our sun is a population 1 star. It has a very small amount of heavy elements, so it's still burning a lot of hydrogen. Population 2, even smaller amounts of heavy elements. And the population 2 stars are in these globular clusters, which kind of form this haze around the galaxy.